In this lesson, we consider the kinetics of nucleophilic substitution reactions, and in doing so, answer the more general question, how can we use kinetics to deduce a reaction mechanism? I want to begin by doing a brief review of what we get out of kinetic experiments. If you do kinetic experiments, which simply means studying how the rate of a reaction changes under different conditions, usually concentrations of reactants and temperature are two things that you vary in kinetics experiments, you get what's called a rate law. And a rate law is a mathematical expression relating the reaction rate to the concentration of each reactant. So for a reaction of the form A plus B goes to products, which is what a nucleophilic substitution reaction falls into, there are three simple possibilities. The first possibility is that the rate remains the same regardless of the concentration of either reactant. The rate law then would just simply be rate is K, rate is a constant, and this is called a zero order rate law because there are zero concentration terms in the rate law. The second possibility is that the rate depends on the concentration of one reactant, but not on the concentration of the other. So the rate law then would be rate equals K, the rate constant, times the concentration of A, or the rate equals K, the rate constant, times the concentration of B. This is called a first order or unimolecular rate law because there is one concentration in the rate law. Then the third possibility would be that the rate depends on the concentration of both reactants. So the rate law for this possibility would be that the rate is equal to K, the rate constant, times the concentration of A times the concentration of B. This is a second order or bimolecular rate law because there are two concentrations, both A and B, in the rate law. So let's look at the SN2 mechanism and try to see how it fits into the paradigm that I've established. The SN2 mechanism has just one step. The reaction takes place when the two reactants collide. If you looked at the curved arrows for the SN2 reaction, Y has to come in and collide with the carbon bearing the leaving group. So as a result, the reaction rate must depend on both the concentration of nucleophile and the concentration of alkyl halide. They have to collide, so if you're going to have more of one of them, you're going to increase the probability of collisions. So therefore, this one-step reaction involving the collision of two molecules must be a second-order reaction. So if you go into the lab, that's our theoretical prediction. Now if you go into the lab and make experimental measurements of the kinetics, that will reveal this to be true. Okay, so if you double the concentration of only the alkyl halide, hold the nucleophile concentration constant, that will double the rate. If you double the concentration of just the nucleophile and hold the alkyl halide concentration constant, that will also double the rate. And if you double the concentration of both reactants, that will quadruple the rate. Therefore, the rate law for an SN2 reaction is the bimolecular rate law. The rate is equal to K times the concentration of alkyl halide times the concentration of nucleophile. And thus, the 2 in the term SN2 refers to second order or bimolecular. What about the SN1 mechanism? Well, the SN1 mechanism, as we saw, is a two-step mechanism. In the first step, you form a carbocation, and in the second step, you have a Lewis acid-base reaction. So we need to consider which of these two steps is the slow step. And chemists also refer to the slow step as the rate-determining step. If a particular reactant is not involved in the slow step, its concentration will not appear in the rate law. Okay, that's very important. I'm going to say it again. If a particular reactant is not involved in the slow step, its concentration will not appear in the rate law. The rate of the overall reaction is only the rate of the slow step. Any steps that are fast are going to be fast relative to the slow step, and they're not going to be limiting the rate of the reaction. Okay, so in step 1, a stable neutral compound, the alkyl halide, is turned into a carbocation that is electron deficient, only 6 electrons around carbon, and has a positive charge, and therefore I think we can safely say that it is unstable, at least relative to the starting material. In step 2, that unstable carbocation is turned into a stable neutral compound with 8 electrons around carbon, no charges on the carbon, everybody goes home happy. Which step is harder to do? First step. Therefore, it is the rate determining step. Is the nucleophile involved in the first step? No. Does its concentration affect the rate of the reaction? No. Therefore, the reaction must be first order in alkyl halide only, and the rate law is rate is equal to K times the concentration of alkyl halide. The 1 in the SN1 reaction stands for first order or unimolecular. In the next lesson, we will go ahead and look at energy diagrams as a way to visualize the progress of these reactions. But for the SN1 reaction, experimental measurements confirm this rate law. The rate doubles if the alkyl halide concentration is doubled, but the rate does not change if the nucleophile concentration is doubled.